Hello. Today we want to present you our project, Reinforcement Learning for E-commerce Recommendations. In the competitive world of e-commerce, array methods like deep Q networks and Actor-Critic models offer a powerful alternative to traditional recommendation systems. This approach dynamically learns from user behavior sequences to optimize long-term engagement and revenue metrics such as CTR, ARPU, and conversion rates. By leveraging deep learning, the policy optimization, our, our system delivers more relevant, timely, and profitable recommendations. Business understanding. E-commerce platforms increasingly use array to overcome delayed feedback, behavior variability, and cold start issues in personalized recommendations. By treating recommendation as a sequential decision task and employing deep Q networks alongside Actor-Critic models, our system dynamically optimizes long-term metrics like CTR, conversion rate, and ARPU, driving sustained user engagement and revenue growth.
The dataset is a comprehensive event log capturing user behavior on a multi-category e-commerce platform. It includes over 20 million real-time recorded events, which are product use, cart additions, and purchases, collected between October 2019 and February 2020. This rich behavioral data is valuable for building recommendation systems, analyzing sales funnels, and predicting purchase intents. The dataset contains detailed interaction records uh, with fields such as event time, event type, product and category IDs, brand, price, user ID, and session ID. Preprocessing included loads the data, remove session with missing IDs and duplicates. Also calculating features such as historical counts and average prices up to each event, and cyclic temporal features, and scaling and encoding. Also, the data set has been enriched with information on holiday days. The resulting data set in database is feature rich, combining session level, user level, product level, category level, and time-based signals.
Okay, what about the problem formulation? We cast recommendation as a Markov decision process, and where the station is a history, some categorical features like brand, or some other information that we have in our data set. Of course, we don't use the action in this part. For the action, we consider some products. We have 30,000 them. We have 30,000 unique products in our data set, and for rewards, we assign plus 0.1 for just view, or for guessing the category, plus 1 for the cart ad, and plus 5 for a purchase. Also, we consider minus 0.5 for an incorrect guess.
We implemented two RL-based recommenders, a deep Q network and Actor-Critic, on top of Shade session transition dataset that turns raw session logs into transition tuples, which are state, next action, reward, next state, and done flag of the user session. Each tuple binds a padded history of the last interactions, a numerical feature vector, which includes price, session length, prior views, cards, purchases, and holiday distance, and etc. Categorical embeddings for products, brand, and holidays, and event-based rewards. And okay, what about DQN, Q function and training process? We approximate Q value with two-layer network on top of a 256-dimensional GRU encoder. Inputs are the concatenated GRU state and feature embeddings. Outputs are Q values for every product. We train using double DQN with a hyper smooth temporal difference loss, gradient clipping also, and periodic target network updates.
So, about architecture and optimization of Actor-Critic, a shared GRU encoder fits into heads, an actor, and a critic. The critic minimizes TD error, while the actor uses advantage weight policy gradients plus an entropy bonus to encourage exploration. And tuning and evaluation, all K hyperparameters are optimized via Aptuna. Final models are evaluated on ranking, classification, and business metrics, with results presented in interactive HTML reports.
And what about the results? We can't say that they are really good, but the results are the results. The Actor-Critic architecture demonstrates superior performance across key business metrics. It achieves the highest average revenue per use and conversion rate, consistent with its theoretical trends in optimizing long-term rewards, especially important in environments with sparse high-value signals like purchases. Its higher outcrock further indicates a more effective ranking policy, likely due to adaptive session modeling via policy gradients. TQN shows marginal advantages in accuracy and diversity scores. And for the random agents, the random baseline performs worst overall, though reveals unexpected insight through its lower diversity score. And for the sake of interesting, we also tried to evaluate the accuracy of guessing the category. There are significantly fewer of them in our dataset, just over 800. For this task, the DQN model shows an accuracy of about 12%.
So, what we want to say in conclusion is that in complex recommendation environments featuring a 30,000 plus product, action space, sparse multimodal rewards, and rich contextual features, the Actor-Critic model showed a little better results than DQN. Actor-Critic handles large action spaces more efficiently, supports continuous decision making, and can directly optimize long-term business goals like revenue and user retention. Thank you for your attention.